Hello, and welcome. Tonight we're going to explore one of the most fascinating concepts in all of science. Something that sounds like pure fantasy but is actually woven into the very fabric of our universe. We're going to talk about time travel, not the Hollywood version with gleaming machines and paradoxes, but the real thing, the kind that happens every single day. All around us, verified by countless experiments and embedded in the technology you probably use today. So settle in somewhere comfortable, let the outside world fade away, and prepare to drift through a different kind of journey. One where the destination isn't just sleep, but a deeper understanding of how strange and wonderful our universe truly is. Time travel is real. It's happening right now, and by the end of our time together tonight, you'll see the world and time itself in an entirely new way. Section 1. The reality of time travel. Let's begin with something that might surprise you. Right now, as you listen to these words, people are traveling through time, not in some distant future or in the pages of science fiction, but actually, measurably, provably moving through time at a different rate than you and me. These time travelers aren't aboard glowing capsules or standing in circles of mysterious energy. They're astronauts orbiting above us on the International Space Station, and they're experiencing time slightly differently than we are here on Earth's surface. This isn't speculation or theory in the abstract sense. It's been measured, it's been calculated, it's been confirmed over and over again with atomic clocks so precise they can detect differences measured in billionths of a second. When astronauts return from 6 months aboard the International Space Station, which orbits at about 7,700 meters per second, they come back having aged slightly less than they would have if they'd stayed on Earth. The difference is tiny, impossibly small in human terms, about 5,000ths of a second, but it's there, real and measurable. Think about that for a moment. Those astronauts, floating in their orbiting laboratory watching the Earth turn beneath them, are not just exploring space, they're traveling into Earth's future, however minutely. When they return and reunite with friends and family, they've experienced slightly less time. Their hearts have beaten fewer times. Their cells have undergone fewer cycles. They are, in the most literal sense possible, time travel. This phenomenon has a name, one that sounds almost musical in its technical precision: time dilation. It was predicted by Albert Einstein in 1905. In what might be the most revolutionary paper in the history of physics. Einstein understood something that defied every intuition humans had developed over millennia of watching the sun rise and set, of counting seconds and minutes and hours. He understood that time is not absolute, it's not the same for everyone. Time is flexible, malleable, dependent on how fast you're moving and where you are in a gravitational field. Before Einstein, time seemed as solid and unchanging as anything could be. 1 second on Earth was 1 second everywhere in the universe. Time marched forward at the same rate for every observer, every atom, every star. It was the great constant, the metronome by which everything else could be measured. But Einstein showed us that this intuition, this feeling of time as universal and uniform, was wrong. Time bends, time stretches, time slows down and speeds up depending on your reference frame. The mathematics that describe this are elegant in their simplicity, at least in form, though the implications ripple outward into territories that challenge everything we thought we knew about reality. The faster you move through space, the slower you move through time. at least from the perspective of someone who's stationary relative to you. This isn't some trick of perception or limitation of measuring tool. It's a fundamental feature of the universe itself, as basic as the fact that mass has weight or that light travels in straight lines through empty space. Everyday technology that billions of people depend on requires corrections for time dilation. Your smartphone, when it uses GPS to tell you where you are and how to get where you're going, is constantly accounting for the fact that time moves differently for the satellites overhead than it does for you standing on the street. Those satellites, orbiting at about 20,000 kilometers above Earth's surface, each carry atomic clocks of extraordinary precision. These clocks, which can keep time to within nanoseconds, would drift out of sync with ground-based clocks if we didn't account for relativity. The situation with GPS satellites is actually wonderfully complex, because two different relativistic effects are at play simultaneously, pulling in opposite directions. Because the satellites are moving fast relative to Earth's surface, about 14,000 kilometers per hour, special relativity predicts their clocks should run slow, losing about 7 microseconds each day. But because they're farther from Earth's gravitational field, experiencing weaker gravity than we do down here, general relativity predicts their clocks should run fast, gaining about 45 microseconds per day. The net effect is that satellite clocks gain about 38 microseconds daily, compared to clocks on the ground. 38 microseconds might not sound like much. It's 38 millionths of a second, a duration so brief that nothing in human experience can really capture it. But light travels fast, astonishingly fast, covering about 300,000 kilometers every second. In 38 microseconds, light travels about 11 kilometers. If we didn't correct for this relativistic time difference, your GPS would be off by kilometers after just a single day. Within a week, it would be useless. The navigation system in your car, the map on your phone, the precise timing systems that coordinate global communications and financial transactions, all of these depend on engineers accounting for the reality of time travel. Think about what this means. Every time you check your location on a map, every time you get directions to a restaurant or find your way home from somewhere unfamiliar, you're benefiting from our understanding that time is not absolute. The system works because we've built corrections for time dilation right into it. Before the GPS satellites were even launched, engineers deliberately set their onboard clocks to tick at a slightly different rate, 10.22999999543 MHz, instead of the standard 10.23 MHz. This pre-adjustment compensates for the relativistic effects the satellites will experience once they're in orbit, ensuring that from our perspective on the ground, their clocks appear to tick at the correct rate. This isn't just about satellites and astronauts though. Time dilation has been measured in experiments here on Earth. Tests so precise and so carefully controlled that they leave no room for doubt. In 1971, physicists J. Theli and Richard Keating took 4 cesium atomic clocks aboard commercial airliners and flew them around the world, both eastward and westward. When they compared these flying clocks to identical clocks that stayed on the ground, they found exactly the differences that Einstein's equations predict. The eastward flying clocks, moving with Earth's rotation and thus traveling faster relative to an inertial reference frame, lost about 59 nanoseconds. The westward flying clocks, moving against Earth's rotation, gained about 273 nanoseconds. Every nanosecond matched the predictions. Even more striking are experiments with particles called muons. These are unstable particles created high in Earth's atmosphere when cosmic rays collide with air molecules, Muons have a very short lifetime, decaying in about 2 microseconds when at rest. Given how fast they travel, simple arithmetic would suggest they shouldn't be able to reach Earth's surface before decaying, but they do reach the surface in large numbers, and we detect them constantly. The reason is time dilation. From our reference frame, the muons' clocks are running slow because they're moving at near light speed, close to 99.8% of light's velocity. Their 2 microseconds stretch out to 30 microseconds or more, giving them plenty of time to complete their journey. From the muons' perspective, if they could have one, their clocks are running normally, but the distance they need to travel has contracted. Either way you look at it, relativistic effects are at work, proven by the simple fact that these particles reach detectors on the ground. In particle accelerators like the Large Hadron Collider, time dilation isn't just observable, it's an everyday operational reality. Particles whip around the accelerator ring at speeds so close to light speed that the difference is negligible for most purposes. At these velocities, time dilation becomes extreme. Particles that would normally decay almost instantly survive for thousands of times longer from our perspective. Physicists routinely calculate exactly how long particles will live based on their velocities, and the measurements match Einstein's predictions to extraordinary precision. Some experiments have confirmed time dilation to better than 1 part in 1,000, meaning the theory is accurate to within 0.1%. So when we say time travel is real, we're not speaking metaphorically or engaging in wordplay. We mean it literally. People traveling at high speeds age more slowly than people at rest. Clocks moving rapidly tick at different rates than stationary clocks. Time itself passes differently depending on your motion and your position in a gravitational field. This is simply how the universe works. It's been tested, confirmed, and utilized in practical technology that surrounds us. The time travelers are real. They just don't match the popular imagination of what a time traveler should be. They're astronauts, particles, satellites, anyone or anything moving at speeds that make relativistic effects noticeable. Consider the remarkable precision with which these effects have been measured. Modern atomic clocks can detect time differences so small they boggle the mind. The current generation of optical lattice clocks, which trap atoms in standing waves of laser light, can measure time to an accuracy of 1 part in 10 to the 18th, which means they would neither gain nor lose a second over the entire current age of the universe. With such instruments, physicists have measured gravitational time dilation over height differences of mere centimeters. In one extraordinary experiment conducted in 2010, researchers at the National Institute of Standards and Technology in Boulder, Colorado, used aluminum-ion clocks to measure time dilation effects between clocks separated by just 33 centimeters. One clock sat on a table, the other on a platform slightly higher. The difference in gravitational potential, tiny as it was, caused the upper clock to tick faster by about 4 parts in 10 to the 17th. This means that if you stood on a ladder for your entire life, you'd age very slightly more than someone who stayed on the ground. The difference would be measured in nanoseconds over a lifetime, completely imperceptible to human experience, but real and measurable with precise enough instruments. The same experiment also measured velocity-based time dilation. By moving one clock at speeds of just a few meters per second, speeds you'd experience riding a bicycle, they detected the predicted time dilation effect. The moving clock ran slower by an amount precisely matching Einstein's equations. This wasn't some exotic high-energy physics experiment. It was everyday motion, walking or cycling speeds. Yet time dilation was there, ticking away in the background of reality. These experiments tell us something profound. Time dilation isn't some abstract theoretical prediction that only manifests in extreme conditions. It's happening all around us, all the time, in every moving object at every altitude. It's just that the effects are normally so tiny that we never notice them without extraordinarily precise measuring tools. Our senses evolved to navigate a world where velocities are tiny compared to light speed, and where gravitational variations across human scale heights are negligible. So we perceive time as absolute. But that perception is an artifact of the limitations of our biological senses. The practical applications extend beyond GPS. Any system that requires precise timing must account for relativistic effect. The global financial system, for instance, depends on synchronized clocks across different time zones and altitudes. High-frequency trading, where transactions happen in microseconds, could theoretically be affected by time dilation if precision weren't maintained. Communications networks, power grids, scientific experiments, all of these rely on timing systems that incorporate relativistic corrections. There's something almost magical about the fact that our modern world, with all its technology and precision, rests on an understanding of time that Einstein revealed over a century ago. Every time you use your phone to navigate, you're benefiting from our knowledge that time is relative. Every time physicists collide particles in an accelerator, they're confirming that moving clocks run slow. Every time astronomers observe a distant supernova or gamma-ray burst, they're working with light that has traveled through space-time that might be warped by gravitational fields, affecting not just the path of the light but the timing of the signals they receive. And there's a human element to this that's worth contemplating. Scott Kelly, the astronaut who spent nearly a year aboard the International Space Station, returned to Earth having aged slightly less than his twin brother Mark, who stayed on the ground. The difference was measured in milliseconds, 5 milliseconds to be precise. This is far too small for either twin to notice subjectively. Scott didn't return feeling younger or perceiving that less time had passed. His experience of the year was the same as Mark's experience of the year, moment by moment, heartbeat by heartbeat. But objectively, measurably, Scott experienced less time. Fewer oscillations occurred in his atoms. Fewer quantum events transpired in his body. If we had perfect records of every particle interaction in both twins' bodies, we'd find that Scott had experienced fewer interactions, fewer moments than Mark. This is what time travel means at the practical level. Not dramatic jumps through time. Not the sensation of minutes passing while years fly by outside, but a subtle, almost imperceptible shift in the rate at which you move through time, relative to others. And yet, despite being subtle, it's undeniably real. If we could build spacecraft capable of reaching velocities approaching light speed, the effect would no longer be subtle. It would be dramatic, life-changing, allowing travel across cosmic distances within a human lifetime. The physics permits it. The universe allows it. The only barrier is engineering, the practical challenge of building ships that can reach such speeds and sustain them safely. And here's something even more profound to consider as you drift deeper into relaxation. This means that your future is not the same as someone else's future. There is no universal now that extends across the entire cosmos. An event that you see as happening right now might be in the past from one reference frame and the future from another. The very concept of simultaneous events occurring at the same moment breaks down once you account for relativity. Two people moving at different speeds will disagree about whether distant events happened at the same time, and neither of them is wrong. They're just experiencing different slices through the four-dimensional structure we call space-time. This revelation, this understanding that time is relative, represents one of the deepest shifts in human comprehension of the universe. For thousands of years, humans looked up at the sky and imagined time as a great river, flowing uniformly past all things, carrying everything from past to future at the same relentless pace. Einstein showed us that this image is wrong. Time is more like an ocean, with currents that flow at different speeds depending on where you are and how you're moving. Some currents rush swiftly forward, others drift slowly. And navigating from one to another means experiencing time differently than those in different currents. Section 2: Einstein's Revolution. To truly understand how time travel works, we need to go back to 1905, a year that seems impossibly distant now, but one that fundamentally changed everything about how we understand reality. In that year, a young patent clerk in Bern, Switzerland, a man whose university career had been undistinguished and whose employment prospects seemed limited, published a paper that would reshape physics. His name was Albert Einstein, and the paper was titled On the Electrodynamics of Moving Bodies. Later, the world would come to know the ideas in this paper as the special theory of relativity. Einstein started from a simple observation, one that had puzzled physicists for years. Light behaves strangely, unlike sound which needs air to travel through, or waves in water that need water as their medium. Light doesn't seem to need anything. It travels through the vacuum of space, through the void between stars, seemingly without support from any underlying substance. More puzzling still, experiments suggested that light always traveled at the same speed, regardless of how the source or observer was moving. This violated intuitions built up from everyday experience with baseballs and cars and everything else that moved. Imagine throwing a ball forward while riding in a moving car. From the perspective of someone standing on the sidewalk, the ball's speed is the combination of your throwing speed and the car's speed. If you throw at 20 kilometers per hour while the car moves at 50 kilometers per hour, the ball moves at 70 kilometers per hour relative to the ground. This is how we expect velocities to add. It's so natural, so obvious from daily life, that it seems absurd to question. But light doesn't work this way. If you shine a flashlight forward while riding in a fast-moving spacecraft, the light doesn't travel at the speed of light, plus the speed of your spacecraft. It just travels at the speed of light, about 300,000 kilometers per second, no more, no less. Someone standing still outside your spacecraft would measure the light at exactly the same speed. This seems impossible. It violates common sense. How can something always have the same speed regardless of how fast its source is moving? Einstein's great insight was to take this impossible-seeming fact seriously. Instead of trying to explain it away or fit it into existing theories, he asked what would have to be true about the universe for this to make sense. The answer he arrived at was radical. If the speed of light is constant for all observers, then time and space themselves must be flexible. They must adjust, stretching and contracting, to ensure that everyone measures light at the same speed. This leads to a profound realization. Imagine two events happening at different locations. How much time passes between them depends on your motion. If you're moving relative to those events, you'll measure a different time interval than someone who's stationary, and both measurements are equally valid. There's no privileged reference frame, no cosmic clock keeping the true time. Each observer's experience of time is as real and valid as any other's. This is where the famous twin paradox comes in, a thought experiment that perfectly illustrates how strange relativity really is. Imagine twins, one of whom stays on Earth while the other boards a spacecraft capable of traveling at a significant fraction of light speed. The traveling twin zooms off to a distant star and then returns. When they reunite, they find something astonishing. The traveling twin has aged. Perhaps the Earth-bound twin is now 50 years old, while the traveling twin is only 30. This isn't a trick or an illusion. The traveling twin genuinely experienced less time. Fewer of their heartbeats occurred. Fewer thoughts passed through their mind. Less biological aging happened. This seems paradoxical, because you might think from the traveling twin's perspective, the Earth twin was the one moving away at high speed. So shouldn't the Earth twin be the one who aged less? The resolution lies in the fact that the situation isn't truly symmetrical. The traveling twin had to accelerate to reach high speed, then decelerate and turn around, then accelerate again for the return journey. This acceleration breaks the symmetry. The traveling twin's reference frame changed, while the Earth twins remained constant. General relativity, Einstein's extension of special relativity to include acceleration and gravity, accounts for this perfectly. When all effects are properly calculated, both twins agree on their ages when they reunite. The twin paradox isn't just a thought experiment. With modern technology, we can actually observe versions of this effect. Remember those muons we discussed earlier, created high in the atmosphere and reaching the ground despite their short lifetimes. From the muon's perspective, time flows normal. But from our perspective, watching from Earth, their clocks run slow. In a sense, the muon is the traveling twin, moving at near light speed, while we're the stationary twin. When the muon reunites with us by being detected in an instrument on the ground, it has aged less than we would expect if time were absolute. Einstein's special theory of relativity rests on two principles that sound simple but have profound implications. First, the laws of physics are the same in all inertial reference frames. An inertial reference frame is one that's moving at constant velocity, not accelerate. This means that whether you're sitting still or moving steadily at half the speed of light, the fundamental rules governing how the universe works are identical. There's no experiment you can do inside a sealed laboratory to determine your absolute velocity. You can only measure your velocity relative to something else. Second, the speed of light in vacuum is constant for all observers, regardless of the motion of the light source or observer. This constancy of light speed is the key that unlocks everything else. From these two principles, Einstein derived time dilation, length contraction, the relativity of simultaneity, and ultimately the equivalence of mass and energy expressed in that most famous of equations, E equals mc squared. The mathematics of special relativity involves something called the Lorentz transformation, named after Hendrik Lorentz, who developed the mathematical framework before Einstein gave it physical meaning. These equations describe how measurements of time and space transform when you switch between reference frames moving at different velocities. The key factor in these equations is gamma, often written with the Greek letter g, which depends on velocity. For everyday speeds that are tiny compared to light speed, gamma is almost exactly 1, meaning relativistic effects are negligible. This is why we don't notice time dilation in daily life. But as velocity approaches light speed, gamma grows dramatically, approaching infinity as you get closer and closer to light speed. This mathematical structure, beautiful and precise, tells us something profound about the universe. Space and time are not separate, independent entities. They're interwoven into a single four-dimensional fabric called space-time. When you move through space, you're also moving through time, and how you move through one affects how you move through the other. Everything in the universe, including you right now, is moving through space-time at the speed of light. Yes, you read that right. Even sitting still in space, you're rocketing through time at light speed. When you start moving through space, some of your motion through time gets converted to motion through space, which is why time slows down for you relative to someone who remains still.
Think of it this way. Imagine space-time as having four dimensions. The three spatial dimensions we're familiar with: up, down, left, right, forward, backward, and one time dimension. Your total velocity through this four-dimensional space-time is always the speed of light. If you're not moving through space at all of your motion is through time. You're aging at the maximum rate, experiencing 1 second per second. But if you start moving through space approaching light speed, more of your total motion is through space and less is through time. You age more slowly. At light speed, if you could reach it, which you can't if you have mass, all your motion would be through space and none through time. Time would stop for you entirely. This is why light itself doesn't experience time. From a photon's perspective, if such a perspective makes sense, zero time passes during its journey from the moment it's emitted to the moment it's absorbed, whether that journey takes nanoseconds or billions of years from our perspective. This interweaving of space and time has another consequence that's just as strange as time dilation: length contraction. Objects moving at high speeds are actually shorter in the direction of motion than they are at rest, but only from the perspective of an observer relative to whom they're moving. A spacecraft zooming past you at 90% of light speed would appear squashed, compressed along its direction of travel. But from the spacecraft's perspective, it's perfectly normal, and you and everything in your reference frame are the ones that appear compressed. The universe revealed by special relativity is far stranger than the one we evolved to perceive. Our intuitions about time developed in a realm where speeds are tiny compared to light speed, where relativistic effects are so small they're completely undetectable without extraordinarily precise instruments. For survival on the African savanna, knowing that time might tick slightly differently for a running antelope versus a resting one would have provided zero advantage. So we evolved to perceive time as absolute, as a universal backdrop against which events unfold at the same rate for everyone. Special relativity tells us this perception, while useful for daily life, is fundamentally incorrect. Einstein published his special theory at age 26, an age when many physicists are still working on their graduate study. The paper, written in clear German prose without a single reference to other work, emerged seemingly fully formed. But Einstein had been pondering these questions for years, conducting what he called thought experiments. Imagining riding alongside a beam of light or observing lightning strikes from moving train. These mental exercises, combined with deep knowledge of electromagnetism and classical mechanics, led him to conclusions that contradicted centuries of accumulated wisdom, but aligned perfectly with experimental evidence. The scientific community's reaction was mixed. Some immediately recognized the brilliance and importance of Einstein's work. Others remained skeptical, unable to let go of cherished notions about absolute time and space. But as experimental evidence accumulated, as more precise measurements confirmed the predictions, skepticism gave way to acceptance. By the 1920s, Einstein was world famous, his name synonymous with genius.
His theory of relativity considered one of the crown jewels of modern physics. And yet, special relativity was just the beginning. As profound as it was, as much as it revolutionized our understanding of time and space, it had a limitation. It only dealt with constant velocities, with observers moving in straight lines at steady speed. It said nothing about acceleration or gravity. That gap would be filled by Einstein's next masterpiece, the general theory of relativity, which extended these insights to include warped space-time, gravitational time dilation, and possibilities even stranger than special relativity suggested. Section 3. Moving through time. Now let's explore what happens when we push velocities toward their limit. When we approach the speed of light and time dilation becomes not just measurable but dramatic. This is where the real magic of time travel emerges, where the effects become large enough that a human could experience them subjectively, where the future opens up as a destination that's actually reachable. Imagine building a spacecraft capable of sustaining acceleration at 1 g, the same acceleration you feel from Earth's gravity. This would be comfortable for humans. You'd feel normal weight the entire journey, able to move around as easily as you do on Earth's surface. Now imagine this spacecraft accelerating continuously at 1 g for an extended period. The speeds you could reach are mind-boggling. After 1 year of constant acceleration at 1 g, you'd be moving at speeds close to light speed. Not quite there, because as you approach light speed, it becomes harder and harder to accelerate further, requiring more and more energy. But you'd be going fast enough that time dilation would be significant. From your perspective aboard the ship, time would flow normally. You'd eat meals, sleep, wake up, experience seconds and minutes and hours at their usual pace. But back on Earth, time would be racing forward. Days would pass in the time you experienced as hours, weeks in what felt like a day. Keep accelerating, keep pushing, and the effect grows more extreme. After several years of ship time, decades could pass on Earth. Continue long enough, and centuries slip by back home while you age normally. The mathematics describing this are precise and unforgiving. The Lorentz factor, that gamma we mentioned, grows without limit as velocity approaches light speed. At 90% of light speed, gamma is about 2.3. For every year you experience, about 2.3 years pass on Earth. At 99% of light speed, gamma is 7. At 99.9%, it's 22. At 99.99%, it's 70. This leads to an astonishing realization. With sufficient technology, humans could travel to distant stars, to the far side of our galaxy, even to other galaxies, all within a human lifetime as experienced by the travelers. The trick is acceleration. Keep accelerating at 1 g for long enough, and the galaxy opens up. Of course, the travelers would return to an Earth that had aged thousands or millions of years in their absence. They'd be time travelers into Earth's far future, unreachable in any other way. Let's make this concrete with specific numbers. Imagine a journey to the nearest star system, Alpha Centauri, about 4.4 light-years away. If you could somehow travel at 99% of light speed, the journey would take you about 4.4 years from Earth's perspective. But from your perspective aboard the ship, thanks to time dilation, the journey would take only about 8 months. You'd step off the ship having aged 8 months, while your twin back on Earth aged 4.4 years. Or consider a more ambitious journey. The center of our Milky Way galaxy is about 26,000 light-years away. If you could travel at speeds just slightly below light speed, say at gamma equals 1000, you could reach the galactic center in just 26 years of ship time. 26 years of your life to cross a distance that light takes 26,000 years to traverse. From Earth's perspective, yes, 26,000 years would pass. But from your perspective, you'd have traversed the galaxy in less time than it takes for a human generation to pass. These aren't just fantasies. The physics is sound, confirmed by every experiment we've ever done. The only limitation is practical. Building a spacecraft that can accelerate to such speed. The energies required are enormous, beyond anything our current technology can provide. But they're not forbidden by any law of physics. It's an engineering challenge, not a fundamental impossibility. Particle accelerators give us a glimpse of what's possible. The Large Hadron Collider accelerates protons to 99.999999% of light speed. At this velocity, the proton's gamma factor is about 7,000. Time passes 7,000 times slower for them than for us. A proton living its 2 microsecond lifetime could zip around the entire 27-kilometer ring over 10,000 times before decaying. From the proton's perspective, its lifetime is normal, but the ring has contracted to just a few meters in the direction of travel. Every day in labs around the world, physicists accelerate particles to relativistic speeds and observe time dilation firsthand. The particles live longer than they should. Their internal clocks, the quantum processes that govern their decay, run slower from our perspective. This isn't theory or speculation. It's experimental fact, observed countless times, forming the basis for entire fields of particle physics. But particles aren't people. The practical challenge of human time travel via velocity isn't just reaching high speeds, it's sustaining them safely and comfortably. Spacecraft would need protection from cosmic rays and interstellar dust. Colliding with even a small particle at near light speed would release devastating energy. Shielding would be essential. Life support systems would need to function perfectly for years or decades, and the energy requirements are truly staggering. Consider the energy needed to accelerate a spacecraft. The relativistic kinetic energy formula shows that as you approach light speed, the energy required approaches infinity. This isn't just because you're going faster. As Einstein showed, energy and mass are equivalent. E equals mc squared. When you add energy to accelerate an object, you're literally adding mass to it. The closer you get to light speed, the more massive the object becomes, requiring ever more energy to accelerate further. This creates a barrier. Nothing with mass can actually reach light speed, because doing so would require infinite energy. Yet despite this barrier, the possibility remains. Tantalized fusion drives, antimatter engines, light sails pushed by powerful lasers. These and other speculative technologies might someday make interstellar voyages at relativistic speeds possible. Projects like Breakthrough Starshot, which envisions tiny probes accelerated to 20% of light speed by ground-based lasers, show that serious scientists and engineers are thinking about these challenges. The probes themselves wouldn't experience dramatic time dilation at just 20% of light speed, but they represent a first step toward faster journeys. There's something poetic about time dilation as a gateway to the stars. The universe's vast scales, the distances between stars measured in light years, seem to doom us to our local neighborhood. Even traveling at light speed, which we cannot do, it would take years to reach nearby stars, decades to cross a good fraction of the galaxy, millions of years to reach distant galaxies. These timescales make interstellar travel seem hopeless for beings with human lifespan. But time dilation changes the equation. From the perspective of a traveler moving at near light speed, distances contract and journeys shorten. What looks like an impossible gulf to those left behind becomes a manageable voyage for those making the journey. The universe remains vast, but it becomes traversable in human timescales for those willing to leave their own time behind, to arrive in the future of those they left. This creates a profound asymmetry. You can travel to the future, but you can't go. The astronauts aboard a relativistic spacecraft could visit humanity's descendants thousands or millions of years hence, but they could never return to their own time. Every journey forward is one way. The past remains forever out of reach, at least through this mechanism. And there's another consideration, one that's more philosophical but no less important. If you traveled at near light speed to a distant star and returned, you'd find Earth changed in ways you couldn't predict. Languages would have evolved or died out. Civilizations might have risen and fallen. The people you knew would be dead for centuries. Even the geography might be different. Coastlines redrawn by rising seas, or new mountains thrust up by tectonic forces. You'd be a visitor from a distant past, as alien to your own world as any extraterrestrial. This loneliness, this disconnection from the flow of normal time, is the price of being a time traveler. It's why time dilation, despite being real and proven, doesn't quite match our fantasies of time travel. We imagine visiting the past, seeing dinosaurs or meeting historical figures. We imagine visiting the future, then returning to tell others what we saw. But velocity-based time travel is unidirectional. It only goes forward, and once you've gone, there's no coming back. Still, for all these limitations, the fact remains, time travel through velocity is real. It works. We've measured it. And if humanity ever reaches for the stars in earnest, if we build spacecraft capable of crossing interstellar distances, time dilation will be an unavoidable aspect of those journeys. The explorers who venture outward will not just be crossing space but also crossing time, leaping forward into futures they can visit but never escape.
Section 4. Gravity bends time. Einstein's special relativity revolutionized our understanding of time and motion, but it had an obvious gap. It only worked for constant velocities, for observers moving in straight lines at steady speeds. The real universe is messier. Things accelerate, things orbit, and most importantly, gravity exists. Special relativity said nothing about gravity, treating it as something to be added later, a correction to be made. But Einstein realized something profound. Gravity wasn't separate from space-time structure. Gravity was space-time structure. This insight led to general relativity, published in 1915, 10 years after special relativity. If special relativity was revolutionary, general relativity was transcendent. It replaced Newton's picture of gravity as a force pulling objects together with a geometric picture, where mass and energy curve the fabric of space-time itself. Objects don't fall because gravity pulls them down. They follow the straightest possible paths through curved space-time. And those paths appear curved to us. John Wheeler, a physicist who did much to popularize and extend Einstein's work, captured the essence of general relativity in a single sentence. Space-time tells matter how to move. Matter tells space-time how to curve. Mass and energy warp space-time, creating curves and valleys in the four-dimensional fabric. Other objects moving through this warped space-time follow paths determined by the curvature. Near a massive object like Earth, space-time curves steeply. Objects released from rest follow paths that lead them downward, what we call falling. The Moon orbits Earth, not because a force pulls it around, but because it's following a curved path through Earth's warped space-time. This geometric view of gravity has profound implications for time. Just as velocity affects the passage of time, so does position in a gravitational field. The stronger the gravitational field, the more slowly time passes. This is gravitational time dilation, distinct from but related to the velocity-based time dilation we discussed earlier. To understand gravitational time dilation, imagine two identical clocks, one on the ground floor of a tall building and one on the top floor. The clock on the ground floor experiences slightly stronger gravity than the one on top because it's closer to Earth's center. According to general relativity, the ground floor clock runs slightly slower. If you could compare them after years of operation, the ground floor clock would be behind. The effect is tiny for ordinary buildings, utterly negligible for human experience. But it's there, real and measurable. In fact, it has been measured. Experiments using extraordinarily precise atomic clocks have detected gravitational time dilation over height differences of just 33 centimeters, about 1 foot. Take two identical atomic clocks, place one 33 centimeters above the other, and after enough time, they'll show different time. The lower clock runs slower by about 4 parts in 10 to the 17th, an almost inconceivably small amount, but modern atomic clocks are so precise they can detect even this. The same effect that makes GPS satellites necessary to account for time dilation has a gravitational component. We mentioned earlier that GPS satellites gain about 38 microseconds per day compared to clocks on Earth's surface. Part of this gain, about 45 microseconds per day, comes from gravitational time dilation. The satellites are farther from Earth, in a weaker gravitational field, so their clocks run faster than ours. This effect partially cancels the velocity-based time dilation, which makes their clocks run slower by about 7 microseconds per day. The net result is that gain of 38 microseconds. Gravitational time dilation becomes more extreme as gravity gets stronger. On the surface of a neutron star where gravity is phenomenally intense, time runs significantly slower than in Earth's gravitational field. If you could somehow survive on a neutron star's surface, you'd age much more slowly than people in orbit above you or far away in normal space. And near the ultimate gravitational extreme, a black hole, time dilation becomes infinite. Black holes are regions where space-time curves so severely that nothing, not even light, can escape once it crosses a boundary called the event horizon. At the event horizon, time dilation becomes infinite from the perspective of a distant observer. If you watched someone fall toward a black hole, you'd see them slow down as they approached the event horizon, moving slower and slower, time appearing to grind nearly to a halt. From your perspective, they never quite reach the horizon. They freeze there, eternally falling, their image redshifted and dimmed until it fades from view. But from the falling person's perspective, something very different happens. They cross the event horizon in finite time, experiencing no special moment, no boundary marking the point of no return. They just keep falling, pulled by tidal forces that grow increasingly extreme, until they're torn apart and crushed in the singularity at the black hole's center. The time they experience between crossing the event horizon and reaching the singularity depends on the black holes. For a stellar mass black hole, it might be milliseconds. For a supermassive black hole, the kind at the center of galaxies, it could be hours or days. This extreme time dilation near black holes makes them natural time machines of a sort. If you could survive close to a black hole's event horizon,
orbiting just outside it, time would pass much more slowly for you than for the rest of the universe. Spend what feels like a year there and centuries could pass elsewhere. Of course, the engineering challenges are absurd. The tidal forces near black holes are lethal. Radiation from infalling matter would be deadly, but purely from a time travel perspective, black holes offer the most extreme time dilation effects possible in the universe. The movie Interstellar portrayed this dramatically. Characters visit a planet orbiting close to a massive black hole, where time dilation is so extreme that every hour on the planet corresponds to 7 years back home. When they return from a brief visit, decades have passed. This isn't science fiction, not really. The math works out. Near a sufficiently massive black hole spinning fast enough to allow stable orbits close to the event horizon, time dilation of this magnitude is possible. The movie consulted with physicist Kip Thorne to get the physics right, and while some details were simplified for dramatic effect, the core concept is sound. Gravitational time dilation means that if you want to travel to Earth's far future, you don't necessarily need to reach velocities close to light speed. You could theoretically park yourself near a black hole, wait there for what feels like a short time, then return to find Earth aged far beyond your brief wait. Of course, this requires being able to enter and exit the black hole's vicinity, which involves all the velocity-based concerns we discussed earlier, and it requires surviving the environment, which is hostile beyond description. But the principle holds. There's something deeply strange about all this. Time, which seems so uniform and absolute from our everyday perspective, is actually incredibly variable. It flows at different rates depending on where you are and how you're moving. Every object in the universe has its own clock, its own experience of duration, and these clocks all tick at different rates. There's no master clock, no universal now that everyone shares. General relativity also predicts even stranger phenomena. In certain solutions to Einstein's equations, space-time can curve back on itself in ways that create closed time-like curves, paths, through space-time that loop back to earlier times. These solutions, like the Gödel metric and certain rotating black hole solutions, suggest that backward time travel might be possible. We'll explore these ideas more deeply later, but for now note that they all require extreme conditions that likely don't exist naturally in our universe. What general relativity definitely allows, what we've confirmed through countless experiments and observations, is forward time travel through gravitational time dilation. We can't yet build spacecraft to take advantage of this, can't yet send humans to orbit near black holes or neutrons, but the physics is there, solid and reliable. The universe provides mechanisms for time travel into the future. Both velocity and gravity can slow your clock relative to others, allowing you to reach future times without experiencing their full duration. And here's something worth pondering as you relax into sleep. Every moment of your life you're in a gravitational field. Earth's gravity pulls on you, warping the space-time around you, affecting the passage of time for you compared to someone in deep space far from any gravitating mass. The difference is tiny, but it's there. You age slightly more slowly than you would in the absence of gravity. Living on Earth's surface, you experience time at a rate different from astronauts in orbit, different from satellites overhead, different from travelers between stars. This means your experience of time is unique. No two people, even standing side by side, experience time at exactly the same rate, because they're at slightly different positions in Earth's gravitational field. Their atoms distributed differently in space. The differences are far too small to measure or matter, but they're philosophically profound. Each of us moves through time at our own pace, following our own world line through space-time, and no two world lines are identical.
Section 5. The block universe. Now we venture into territory that's more philosophical but no less important for understanding what time really is. We've established that time is flexible, that it passes at different rates for different observers, but this raises a deeper question. What is time itself? Is it something that flows carrying us from past to future? Or is time something else entirely? Something perhaps more like space? Just another dimension in which events are laid out. This question has occupied philosophers and physicists for over a century, and the answer that emerges from relativity is both beautiful and profoundly disturbing. It suggests that the past, present, and future all exist with equal reality, stretched out across space-time like points along a map. This view is called eternalism, or sometimes the block universe model. To understand the block universe, we need to confront a consequence of relativity we haven't fully explored yet: the relativity of simultaneity. In our everyday experience, we think of now as a moment that exists everywhere in the universe simultaneously. Right now, things are happening on Earth, on the Moon, on Mars, in distant galaxies. All these events are occurring now, sharing the same moment of time. But relativity says this picture is wrong. There's no universal now. What counts as simultaneous, what counts as happening at the same time, depends on your reference frame, on your velocity. Two observers moving at different velocities will disagree about whether distant events happen simultaneously, and neither of them is wrong. Both perspectives are equally valid. Imagine two events, one on Earth and one in a distant galaxy. These events are too far apart for light to travel between them in the time interval between their occurrences. In the jargon of relativity, they're space-like separated. For such events, different observers moving at different velocities will disagree about their order. One observer might see event A happen first, then event B. Another observer, moving at a different velocity, might see event B happen first, then event A. A third observer might see them happen simultaneously. This isn't just about perception or the time it takes for light to reach observers. It's fundamental. The events genuinely have different temporal relationships from different reference frames. There's no absolute answer to the question which happened first. The question only makes sense if you specify a reference. This relativity of simultaneity has profound implications. If there's no universal now, if different observers can disagree about what events are happening at this moment, then in what sense does the present have any special status? What distinguishes the present from the past or future? The block universe answers this by denying that the present is special at all. According to this view, all moments of time exist with equal reality. The past hasn't ceased to exist. It's still there, laid out in space-time. The future hasn't yet come into being. It's already there. Wait, you and everyone else are four-dimensional objects, extended in time as well as space. Your world line, the path you trace through space-time from birth to death, exists in its entirety. Every moment of your life, past, present, and future, is equally real. This is a difficult idea to wrap your mind around. It seems to contradict the most basic feature of our experience, the feeling that the past is gone, that the future hasn't happened, that only the present moment is real. We feel ourselves moving through time, progressing from one moment to the next. How can all moments exist equally? The block universe doesn't deny your experience. It just reinterprets it. You experience the present moment as special because you're currently at that point in your world line. Your consciousness, your subjective awareness, is located at this slice through four-dimensional space-time. But just as being at a particular location in space doesn't mean other locations don't exist, being at a particular moment in time doesn't mean other moments don't exist. Think of it this way. Imagine a movie on a film reel. Every frame exists simultaneously on the reel, laid out in sequence. When you watch the movie, you experience one frame at a time, moving through the sequence from beginning to end. But all the frames exist throughout the view. The beginning of the movie doesn't cease to exist when you reach the middle. The end exists even as you watch the beginning. The block universe suggests reality is like that film reel. All of space-time, all events that ever happen or will happen, exist laid out in a four-dimensional structure. Our consciousness moves through this structure, or perhaps our consciousness is extended through it and we only have subjective awareness of one slice at a time, experiencing the illusion of flow, of time passing. But the structure itself is static, unchanging, containing all of history and all of future in a single timeless whole. Many physicists, though not all, accept some version of the block universe as following naturally from relative. If there's no universal present, if simultaneity is relative, then it's hard to see how the present could have special ontological status, could be more real than past or future. The universe simply is, four-dimensionally, and we experience slices of it sequentially. This has implications that many find unsettling. If the future exists just as much as the present, then in some sense everything that will happen has already happened. Your future is already laid out, existing timelessly alongside your past and present. This seems to threaten free will. How can your choices matter if your future is already real, already determined? Philosophers and physicists have debated this for decades. Some argue that the block universe is compatible with free will, because even though your future exists, it exists as a consequence of your choices. The world line that represents your future is shaped by decisions you make, causes you set in motion. Others argue that the block universe, if true, means free will is an illusion, that our sense of choosing is just the subjective experience of following a path that's already laid out. There are alternatives to the block universe. Presentism holds that only the present moment is real, that the past has ceased to exist and the future doesn't yet exist. The growing block theory says that the past and present are real, but the future isn't. Both of these alternatives try to preserve our intuition that time flows, that the present is special, but both struggle to accommodate the relativity of simultaneity. If simultaneity is relative, how can there be a universal present moment? Different observers would have different presents, which seems contradictory if only the present is real. Some physicists and philosophers argue that we should bite the bullet and accept the block universe, strange as it seems. Others propose modifications to relativity or argue that relativity's lessons about simultaneity don't force us to eternalism. The debate continues, unresolved, likely to remain a topic of discussion, as long as humans contemplate the nature of time. What's clear is that time is stranger than our intuitions suggest. Whether or not the block universe is correct,
Relativity shows definitively that time is not the uniform flowing river we perceive. It's flexible, relative, deeply intertwined with space. Our experience of time passing, of moving from past to future, may be just that, an experience, a feature of consciousness rather than a fundamental aspect of reality. And there's something oddly comforting about this, especially as you drift towards sleep. If the block universe is correct, then every moment of peace, joy or contentment you've ever experienced still exists, is still real, laid out in the eternal structure of space-time. The good moments aren't gone, they're there, permanent features of the universe. And the difficult moments, the painful times, while they also persist in the block, are balanced by all the moments yet to come, future experiences that already exist, waiting for your consciousness to reach them. Time may not flow, the present may not be special, but the totality of your existence, your entire world line from birth to death, is a real, permanent feature of the cosmos. You are not a temporary spark soon to be extinguished, but an eternal pattern woven into the fabric of space-time itself. In the block universe, nothing is ever truly lost. All of time exists together, and you exist within it, always and forever, in every moment you ever experience. Consider what this means for memory and identity. In a block universe, your past self isn't gone, replaced by your present self. Your past self still exists, at earlier coordinates in space-time, just as real as your present self. The child you once were, the teenager navigating adolescence, the young adult finding their way. All of these versions of you exist timelessly in the four-dimensional structure. Your consciousness, moving through this structure, experiences them sequentially, but they're all equally real, all permanent fixtures in the cosmic architecture. This perspective can change how you think about loss and change. When someone dies, their world line ends at that point in space-time, but everything they were, every moment they experienced, remains part of the eternal structure. The block universe doesn't erase death or make it less meaningful, but it suggests that existence, once achieved, becomes permanent. The pattern that was a person, the four-dimensional thread they traced through space-time, never ceases to exist in the structure of reality. Some find this view cold or mechanistic, as if reducing human experience to geometric patterns in space-time somehow diminishes it. But others find it deeply comforting, a suggestion that consciousness and experience, once manifest in the universe, become permanent features rather than fleeting ephemera. Your consciousness might only be aware of one slice of your world line at a time, but the whole world line exists, and in that sense you exist across all the time you ever live, simultaneously in all your moments. The block universe also has implications for how we think about change and becoming. In our everyday experience, things change. Caterpillars become butterflies, seeds become trees, children become adults. We think of these as processes unfolding in time, with the earlier state ceasing to exist as it transforms into the later state. But in a block universe, all stages exist simultaneously. The caterpillar exists at its space-time coordinates. The butterfly exists at its coordinates. The transformation is represented by a world line connecting them, but both endpoints are equally real. This might seem to rob change of its meaning. If the butterfly already exists when the caterpillar exists, has the caterpillar really changed? But perhaps this is thinking about it wrong. The thing is the world line itself, the connection between different states. The caterpillar and butterfly are different slices through a single four-dimensional object, an object that is inherently transformative, that is change embodied in space-time. Physicists and philosophers continue to debate these ideas. Lee Smolin, a theoretical physicist, has argued strongly against the block universe, proposing instead that time is fundamental and that laws of physics themselves might evolve. In his book Time Reborn, Smolin argues that treating time as illusory or emergent is a mistake, that the universe is genuinely dynamic, with the present moment being metaphysically special. He suggests that the block universe, while mathematically elegant, fails to capture something essential about reality. Others, like physicist Carlo Rovelli, propose that time is relational and emergent, arising from thermal and quantum processes, rather than being fundamental. In his book The Order of Time, Rovelli argues that time as we experience it, with its flow and direction, emerges from our partial thermodynamic perspective on the universe. Fundamentally, at the level of basic physics, time might be very different from our experience, perhaps not flowing at all, perhaps not even existing as a single unified thing. The debate reflects a deep tension in modern physics. Relativity suggests a block universe, where all times exist, with equal reality. Quantum mechanics, at least in some interpretations, suggests a more dynamic picture where measurement and observation play crucial roles in determining reality. Thermodynamics gives time a direction, an arrow pointing from past to future. How these different perspectives fit together remains an open question, one that a complete theory of quantum gravity might eventually answer. For now, what we can say with confidence is that time is not what it appears to be from our everyday perspective. Whether it exists as a dimension in a static block, or emerges from more fundamental processes, whether the present is special or all times are equally real, time is stranger, more subtle, more deeply woven into the fabric of reality than our intuitions suggest. We move through it, or it moves through us, or perhaps these distinctions themselves are artifacts of a limited perspective. What remains true is that existence unfolds, experiences accumulate, and consciousness traces paths through whatever ultimate structure underlies reality.
As you rest here, drifting between waking and sleeping, between one moment and the next, you're participating in one of the universe's deepest mysteries, the transition from present to past, from now to then seems so natural, so inevitable, that we rarely question it. But physics has taught us to question it, to wonder whether this flow is fundamental or emergent, whether all moments exist together or whether only the present is real. The questions remain open, the answers uncertain, but the inquiry itself has revealed that time is far more interesting than anyone imagined before relativity changed everything. Section 6. Exotic Possibilities. So far, we've discussed time travel that's proven, measured, and understood. Time dilation from velocity and gravity are facts, incorporated into working technology. But what about more exotic forms of time travel, the kind that populate science fiction? What about traveling backward in time, visiting the past, creating paradoxes? Does physics allow this? The answer is complicated, fascinating, and ultimately unsatisfying if you're hoping for a simple yes or no. The equations of general relativity do permit certain exotic solutions that seem to allow backward time travel. These solutions describe bizarre configurations of matter and space-time where paths exist that loop back to earlier times. But whether these solutions correspond to anything that could exist in our actual universe is a different question. One famous example involves wormhole. A wormhole, more formally called an Einstein-Rosen bridge, is a hypothetical tunnel through space-time connecting two distant locations. Imagine folding space-time so that two far-apart points are brought close together, then poking a hole between them. Travel through the hole, and you emerge at the distant location without having crossed the space between. Einstein and his colleague Nathan Rosen described such structures mathematically in 1935. But the solutions they found were non-traversable. They connected two regions of space-time, but anything trying to pass through would be crushed before completing the journey. The wormhole's throat would pinch off faster than light could traverse it. These Einstein-Rosen bridges were more mathematical curiosities than practical shortcuts. Later work, notably by physicists Kip Thorne and Michael Morris in the 1980s, showed that traversable wormholes might be possible if they were held open by exotic matter with negative energy density. Normal matter has positive energy density. It curves space-time inward, creating gravitational attraction. Exotic matter with negative energy density would curve space-time outward, creating a repulsive effect that could hold a wormhole open against the tendency to collapse. Does such exotic matter exist? Quantum field theory suggests that under certain conditions, energy density can be negative relative to the vacuum. The Casimir effect, a real phenomenon measured in laboratories, involves negative energy density between conducting plates, but the amounts are tiny, and it's unclear whether enough negative energy could be accumulated to stabilize a traversable wormhole. Even if you could create a traversable wormhole, could you use it for time travel? Potentially yes, through a clever manipulation. Imagine you have a wormhole with two mouths, one here on Earth and one in space. Now take the space mouth and accelerate it to near light speed, then bring it back. Time dilation means less time passes for the moving mouth than for the stationary one. So now you have a wormhole connecting two locations in space that are also at different times. Enter one mouth, and you emerge from the other mouth at an earlier time. This sounds like a time machine. But there's a catch. Several catches actually. First, you couldn't travel back to a time before the wormhole was created. You could only go back as far as the moment when the time difference between the mouths was established. Second, the wormhole itself might become unstable as soon as you try to send anything through it that allows information from the future to affect the past. Calculations suggest that quantum fluctuations would grow exponentially at the moment of attempted time travel, likely destroying the wormhole. This leads to a famous proposal by Stephen Hawking called the chronology protection conjecture. Hawking suggested that the laws of physics might prevent the creation of closed time-like curves, paths through space-time, that loop back to earlier times. Every time you try to create such a path, something goes wrong. Quantum effects amplify, wormholes collapse, something prevents the time machine from working. Nature, Hawking proposed, protects chronology. We don't know if the chronology protection conjecture is true. We don't have a complete theory of quantum gravity that would let us calculate definitively what happens in these extreme situations. But it's suggestive that every known mechanism for creating a time machine requires conditions that seem practically impossible. Exotic matter with negative energy, infinitely long rotating cylinders, space-time rotating faster than it does anywhere in the observed universe. Another exotic solution involves rotating black holes.
A non-rotating black hole described by the Schwarzschild solution has a point singularity at its center, a place where space-time curvature becomes infinite and our equations break down. But a rotating black hole described by the Kerr solution has a ring singularity, and the interior of a rotating black hole has a region where mathematically closed time-like curves exist. Could you use these closed time-like curves to travel back in time? Again, the answer is complicated. To reach the region with closed time-like curves, you'd first have to survive entering a black hole, which is impossible if you want to communicate your discoveries to the outside world. And the closed time-like curves exist in regions where space-time is so warped, so far from the geometry we're familiar with, that it's unclear whether the concept of past and future even makes sense there. There are other exotic solutions to Einstein's equations that permit closed time-like curves. The Gödel universe, a solution found by mathematician Kurt Gödel in 1949, describes a rotating universe where time travel is possible. But our universe doesn't match the Gödel solution. It's not rotating in the required way. The Tipler cylinder, an infinitely long cylinder of dense matter rotating at nearly light speed, also permits time travel. But infinitely long objects don't exist in our universe. All these exotic solutions share a common feature. They require conditions that either don't exist in nature or can't be practically created. This might be a coincidence, or it might be a deep principle. Perhaps the universe simply doesn't allow closed time-like curves to form from physically reasonable initial conditions. Perhaps chronology is protected not by a specific mechanism, but by the collective effect of various physical laws conspiring to prevent time machine. If backward time travel were possible, it would create serious paradoxes. The famous grandfather paradox imagines traveling back in time and preventing your grandparents from meeting, thus preventing your own birth. But if you're never born, how could you travel back to prevent their meet? This seems like a logical contradiction. Some physicists and philosophers have proposed resolutions. One idea, the self-consistency principle proposed by Igor Novikov, suggests that if time travel is possible, only self-consistent histories can occur. Any action you try to take in the past must be consistent with the history you already know. You can't kill your grandfather because something will always prevent it. You'll miss, change your mind, or be stopped somehow. The timeline is self-repair. Another resolution involves the many worlds interpretation of quantum mechanics. When you travel back and alter the past, you don't change your original timeline. Instead, you create a new branch, a parallel timeline, where events unfold different. Your grandfather is never born in this new timeline, but in your original timeline, he was born and you descended from him. This avoids logical contradiction, but at the cost of multiplying universes. A third possibility is that quantum effects inherently prevent paradoxes. Calculations by David Deutsch and others suggest that quantum mechanics, combined with closed time-like curves, leads to unique self-consistent solutions that avoid paradoxes. The quantum state of particles traveling around a closed time-like curve would automatically adjust to prevent inconsistencies. But all of this remains highly speculative. We have no experimental evidence for closed time-like curves. We have no way to create them in laboratory. We have no observations suggesting they exist naturally anywhere in the universe. Every exotic solution that permits backward time travel requires conditions we've never seen and may be impossible to create. The most likely conclusion, though not certain, is that backward time travel is forbidden in our universe, not by any single law, but by the combined effect of quantum mechanics, thermodynamics, and gravity. Whenever conditions approach those necessary for a time machine, something prevents it from working. This is admittedly unsatisfying if you are hoping to visit the past, but it maintains the logical consistency of the universe and prevents paradox. Forward time travel, as we've discussed extensively, is definitely possible. Backward time travel remains in the realm of mathematical curiosity, permitted by certain extreme solutions to Einstein's equations, but likely prevented by more fundamental principles we don't fully understand yet. The universe allows us to reach the future faster than normal passage through time would permit, but the past, it seems, remains sealed off, accessible only through memory and historical record. There's something appropriate about this asymmetry. The future is open, reachable, a place we can visit by moving fast or staying near massive objects. The past is closed, unchangeable, a place we can remember but never revisit. This matches our intuitive sense of time's direction, even as time dilation and relativity complicate that intuition in other ways. Section 7. The Arrow of Time. We've explored how time can pass at different rates, how space-time can warp and bend, how the past and future might exist with equal reality in a block universe. But we haven't addressed perhaps the most basic feature of our experience of time, its direction. Time flows forward, never backward. We age, we don't grow young. Eggs break, but never spontaneously reassemble. Stars burn out, they don't ignite from dispersed ashes. There's an arrow to time, pointing unmistakably from past to future. This arrow of time is puzzling, because the fundamental laws of physics don't prefer one direction of time over the other. The equations of quantum mechanics, electromagnetism, and even general relativity are time symmetric or nearly so. If you film particles interacting and play the video backward, the reversed events would still obey the laws of physics. Time reversal is allowed at the microscopic level, and yet at the macroscopic level, the level of everyday experience, time clearly has a direction. This asymmetry is one of the deepest mysteries in physics, touching on thermodynamics, quantum mechanics, cosmology, and the nature of causality itself. Understanding the arrow of time helps us understand why time travel to the past seems forbidden while travel to the future is routine. The most obvious manifestation of time's arrow comes from the second law of thermodynamics, which states that the entropy of an isolated system tends to increase over time. Entropy is often described as disorder, though that's a simplification. More precisely, entropy measures the number of microscopic states consistent with a system's macroscopic properties. High entropy means many possible microscopic arrangements. Low entropy means few. Consider a drop of ink in water. Initially, the ink is concentrated in one spot, a low entropy configuration, because the ink molecules are all in a small region. Over time, the ink spreads out, diffusing through the water until it's evenly distributed. This final state has high entropy, because the ink molecules could be arranged in many different ways while still appearing evenly dispersed. The spreading is spontaneous, driven by random molecular motion, and the process never reverses. You never see dispersed ink spontaneously collect back into a concentrated drop. This increase in entropy gives time its arrow. Low entropy states evolve into high entropy states. The past has lower entropy than the future. When we observe a system, we can often tell which direction time is flowing by watching whether entropy is increasing or decreasing. But why does entropy increase? At the microscopic level, the laws of physics don't prefer high entropy over low. Individual molecules colliding obey time-symmetric laws. The mystery is why macroscopic systems nonetheless show this clear temporal asymmetry. The answer involves statistics and initial condition. While the laws of motion are time-symmetric, the universe started in a very low entropy state shortly after the Big Bang. This initial condition, sometimes called the past hypothesis, is crucial. Given that the universe started with low entropy and that there are overwhelmingly more high entropy states than low entropy states, it's statistically inevitable that entropy increases as the universe evolves. Imagine a box with all gas molecules crowded in one corner. This is a low entropy state. If you let the molecules move randomly, they'll soon spread throughout the box because there are vastly more ways to be spread out than crowded. The spreading is just molecules exploring the available states. And since high entropy states are more numerous, systems naturally evolve toward them. But this explanation raises a deeper question. Why did the universe start with low entropy? We don't know. The low entropy initial state of the universe is one of the great unsolved problems in cosmology. Shortly after the Big Bang, matter and energy were distributed very smoothly, very uniformly, which corresponds to low gravitational entropy. As the universe evolved, gravity caused matter to clump into stars and galaxies, increasing gravitational entropy. The early smoothness, so different from the clumpy universe we see now, set entropy on its increasing trajectory. Some physicists speculate that the low entropy initial condition might be explained by quantum gravity or by cosmological theories involving cycles of expansion and contraction or multiverses. But we don't have definitive answers. What we do have is the observation that given the low entropy start, the second law and the arrow of time follow statistics.
Recently, physicists have explored another aspect of the arrow of time related to quantum mechanics and entanglement. Quantum entanglement occurs when particles interact in ways that link their properties, making the state of the combined system impossible to describe by specifying each particle's state independently. As the universe evolves, interactions create more and more entanglement between subsystems and their environments. This increasing entanglement drives a form of time's arrow related to but distinct from thermodynamic entropy. In quantum mechanics, entropy can be defined in terms of entanglement. A pure state with zero entropy has no entanglement. A mixed state with positive entropy exhibits entanglement with its environment. As systems interact and become entangled with their surroundings, their entropy increases. Research by physicists, including Noah Linden, Sandhu Papasku, Tony Short, and Andreas Winter, has shown that entanglement growth can explain why systems reach thermal equilibrium and why time has a direction at the quantum level. When a system becomes entangled with a large environment, the system itself evolves toward a mixed state that appears to have definite temperature and other thermodynamic properties, even though the combined system and environment remain in a pure quantum state. This entanglement-based arrow of time complements the thermodynamic arrow. Both point in the same direction, from past to future, from low entropy to high entropy. from unentangled states to entangled state, and both ultimately trace back to the initial conditions of the universe, to the mysterious low entropy state shortly after the Big Bang. The arrow of time also connects to causality. We perceive cause preceding effect. You drop a glass and then it breaks. You don't see glass shards spontaneously leap from the floor and assemble into a glass that flies up into your hand. This temporal ordering, cause before effect, seems deeply tied to the entropy gradient. Causes are typically low entropy states or events that lead to higher entropy outcomes. Some physicists have argued that the arrow of time is ultimately an illusion, an artifact of our perspective and memory. Since the fundamental laws are time-symmetric, perhaps the universe itself has no preferred time direction, and the arrow we perceive emerges from our particular situation as subsystems within a larger universe that started with low entropy. Our memories record the past, not the future, because memory formation increases entropy. We remember low entropy states that preceded our current state, but not high entropy states that will follow. This is a subtle point. It's not that events are reversible or that time doesn't have a direction. It's that the direction emerges from statistics and initial conditions rather than from a fundamental asymmetry in the laws themselves. If the universe had started in a high entropy state, entropy might decrease over O, instead of increasing, and the arrow of time would point the other way. Understanding time's arrow is crucial for understanding why time travel to the past is problematic while time travel to the future is straightforward. When you travel to the future via time dilation, you're simply experiencing less proper time than other observers, while the universe's entropy continues to increase around you. You're skipping forward through time, but you're not violating the arrow. Entropy still increases. Causes still precede effects, but traveling backward in time would require moving against the entropy gradient, going from high entropy to low entropy states. This is not forbidden absolutely, but it's extraordinarily unlikely without massive coordinated manipulation of the environment. And if you traveled back and changed things, you'd be creating situations where effects could precede their causes, violating the causal structure that the entropy gradient establishes. This is another reason why backward time travel seems incompatible with the physics of our universe. It's not just the difficulty of creating closed time-like curves or traversable wormholes. It's that moving backward through time would mean moving against entropy's natural flow, against the arrow that points inexorably from past to future. The universe's history is a story of increasing entropy, of spreading complexity, of entanglement growing and energy dispersing. Time travel to the past would be swimming upstream against this cosmic current. The arrow of time also affects our perception of the block universe. If all times exist with equal reality, why do we experience a flow from past to future? Part of the answer may lie in entropy. Our consciousness, our memories, our sense of temporal flow, all depend on systems that are far from equilibrium, systems where entropy is increasing. We remember the past because low entropy states in the past have been encoded in current memory structures. We don't remember the future because future states don't influence current physical states in the same way. So even in a block universe, where all times exist timelessly, the arrow of time remains embedded in the structure. The entropy gradient defines a direction through the block, a preferred way of moving from one slice to another. We experience this gradient subjectively, as times flow, as the progression from past to future. The block itself is static, unchanging, containing all of history and future. But within it,
entropy increases in one direction, and that direction is what we call time. As you drift deeper into restful sleep, contemplate this strange and beautiful fact. The universe has a direction, an arrow pointing from simplicity toward complexity, from order toward disorder, from low entropy toward everything you experience, every memory you hold, every plan you make, is shaped by this arrow. It's why the past is fixed, and the future is open. Why we remember yesterday but not tomorrow. Why time seems to flow rather than sitting static like space. The arrow of time is perhaps the most fundamental asymmetry in nature, and understanding it brings us closer to understanding why the universe is the way it is. Section 8. Time in Quantum Mechanics. As we approach the end of our journey through time, there's one more realm to explore, one where time becomes even stranger and more mysterious than anything we've discussed yet. This is the domain of quantum mechanics, the physics of the very small, where particles exist in superpositions of multiple states, where measurement affects reality, where the classical notion of a particle having a definite position and velocity at each moment breaks down. In quantum mechanics, time plays a peculiar role, different from its role in classical physics or even in relativity. In the standard formulation of quantum mechanics, time is not an observable in the same sense that position or momentum are observable. Instead, time is a parameter that appears in the Schrödinger equation, the fundamental equation describing how quantum states evolve. Time is the independent variable, the thing with respect to which change is measured, but not something that can be measured itself in the quantum sense. This creates puzzles. If time is just a parameter in quantum mechanics, does it have the same fundamental status as space? In relativity, space and time are unified into space-time, treated on equal footing. But in quantum mechanics, they're asymmetric. Space becomes an observable, something quantum uncertain, while time remains classical, definite. Attempts to unify quantum mechanics with general relativity, to create a theory of quantum gravity, must grapple with this asymmetry. In some approaches, time itself becomes quantum mechanical, subject to uncertainty and superposition just like position or momentum. What would it mean for time to be uncertain? How could an event occur at a superposition of different? One of the strangest features of quantum mechanics is entanglement, which we touched on earlier in discussing the arrow of time. When particles become entangled, measuring one instantly affects the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and was deeply uncomfortable with it. It seems to violate the locality principle, the idea that influences should propagate at finite speeds, no faster than light. But quantum entanglement doesn't actually allow faster than light communication. The correlations between entangled particles are real and instantaneous, but you can't use them to send information. The measurement outcomes are random, and while they're correlated with distant measurements, the correlations only become apparent when you compare results later, at speeds limited by light. Still, entanglement raises questions about time and causality. If measurements on entangled particles affect each other instantaneously, does this create causal loops? Can the future affect the past through quantum correlations? Most physicists say no, that entanglement preserves causality despite its non-local feature. The correlations are set up by past interactions, not by future measurements propagating backward in time. But some interpretations of quantum mechanics, particularly those involving backward causation or retrocausality, suggest that future measurements might influence pasts. These interpretations remain controversial, and are not widely accepted, but they indicate how quantum mechanics challenges our understanding of time and causality. There have been experiments exploring what happens when quantum systems interact with closed time-like curves, at least in simulation. In 2014, researchers used photons to simulate quantum particles traveling through closed time-like curves. They found that quantum mechanics can indeed accommodate such scenarios without creating logical paradoxes, at least in the model study. The quantum states adjust in ways that maintain consistency, even when classical reasoning suggests contradictions should arise. This doesn't mean time machines are possible. The experiments simulated closed time-like curves. They didn't create actual paths through space-time that loop back in time, but the results suggest that if closed time-like curves exist, quantum mechanics provides mechanisms for avoiding paradoxes that would doom classical time machines. Another quantum phenomenon relevant to time is decoherence. When a quantum system interacts with its environment, it decoheres, transitioning from a quantum superposition to what appears to be a definite classical state. Decoherence happens because the system becomes entangled with many degrees of freedom in the environment, spreading the quantum information out irreversibly. Decoherence is intimately connected to the arrow of time. The process is irreversible in practice, even though the underlying quantum evolution is reversible in principle.
There's also the question of quantum measurement and time. In the Copenhagen interpretation of quantum mechanics, measurement causes the wave function to collapse, selecting one outcome from many possibilities. This collapse is instantaneous, happening at a definite moment. But when exactly does collapse occur? How long does it take? The measurement problem, as it's called, involves deep questions about the nature of time in quantum processes. Some interpretations, like the many worlds interpretation, eliminate collapse entirely. In this view, all possible measurement outcomes occur, but in separate branches of the universal wave function. Each observer experiences one outcome, but all outcomes happen, creating a branching structure through time. This interpretation makes time even more complex, with multiple futures constantly branching from each present moment. Recently, there's been research into what's called the Page-Wouters mechanism, a way of understanding time in quantum mechanics through correlation. In this framework, time is relational, emerging from correlations between a system and a reference system that serves as a clock. Different observers using different reference clocks will perceive time differently, much as in relativity, but now the effect is quantum mechanical rather than relativistic. This approach might help unify quantum mechanics with relativity by treating time as fundamentally quantum and relational, rather than absolute and classical. It's still a developing area of research, with many open questions and competing proposals, but it represents an attempt to take seriously the idea that time at the most fundamental level is not the simple parameter of the Schrödinger equation, but something more intricate, something woven into the structure of quantum correlation. What emerges from all this is a picture of time as deeply strange. At the quantum level, it's not just that time passes at different rates as relativity shows, it's that the very concept of time as a cleanly defined moment-to-moment progression breaks down when you probe deeply enough. Time becomes fuzzy, uncertain, emergent from more fundamental quantum correlations. For practical purposes, at the scales of everyday life and even for most physics, time remains the parameter we're familiar with. Clocks tick, events succeed one another, causes precede effects. But underlying this familiar structure is a quantum realm, where time's nature becomes mysterious.
where perhaps the distinction between past, present, and future is itself emergent from quantum entanglement and decoherence. As you sink deeper towards sleep, let these ideas wash over you without striving to grasp them completely. Time is mysterious. At the human scale, it's the familiar flow from past to future, the medium through which we live our lives. At relativistic speeds or in strong gravitational fields, it becomes flexible, passing at different rates for different observers. At the quantum scale, it becomes something else entirely, perhaps emergent, perhaps irrelational, perhaps intertwined with the very process of observation and measurement. We don't have all the answers. Physics is still struggling to understand time fully, to unify the different pictures that emerge from relativity, quantum mechanics, and thermodynamics. But we've learned enough to know that time is far richer and stranger than it appears to our limited senses. And we've learned that time travel, at least into the future, is not fantasy, but physics, proven by experiments and incorporated into technology. Conclusion. So we've traveled together through the science of time travel, exploring terrain that ranges from the proven and practical to the exotic and speculative. Let's gather the threads together as we come to rest. Time travel is real. This isn't hype or exaggeration. People traveling at different speeds or positioned in different gravitational fields experience time at different rates. Astronauts aboard the International Space Station age more slowly than people on Earth's surface. GPS satellites must have their clocks adjusted to account for relativistic effects. Particles in accelerators live longer than they should. These effects are measured, confirmed, and utilized in working technology. The mechanism behind time travel is time dilation, a consequence of Einstein's theories of relativity. Special relativity shows that moving clocks run slowly. The faster you move through space, the slower you move through time, at least from the perspective of someone stationary relative to you. General relativity adds that gravity also affects time's passage. Stronger gravity means slower time. Near massive objects like planets or extreme objects like black holes, time dilation can become dramatic. Time dilation only allows travel into the future, not the past. You can age less than others, reaching future times without experiencing their full duration, but you can't go back. The past remains sealed off, accessible only through memory. This asymmetry aligns with the arrow of time, the thermodynamic gradient that points from low entropy past to high entropy future. The philosophical implications are profound. Relativity suggests that time might not flow as we perceive. All moments might exist with equal reality in a block universe, with our sense of progression from past to future being a feature of consciousness rather than fundamental reality. Or perhaps the present is special and the block universe is wrong. But then we must grapple with the relativity of simultaneity and the lack of a universal now. More exotic possibilities, wormholes, closed time-like curves, backward time travel, remain speculative. The equations permit certain strange solutions, but whether these correspond to physical realities is unclear. Most physicists suspect that something, perhaps chronology protection, perhaps the requirements for exotic matter, perhaps quantum effects we don't fully understand, prevents these extreme forms of time manipulation. What's certain is that our intuitions about time are wrong. Time is not absolute. It's not the same for everyone. It's woven together with space into a four-dimensional fabric that can bend, stretch, and warp. Understanding this doesn't just change how we think about time travel. It changes how we think about reality itself. And in practical terms, these insights have already changed technology. Every GPS satellite, every particle physics experiment, Every precision timing system depends on accounting for relativity. The universe we live in is a relativistic universe, and anyone working with high speeds, precise timing, or strong gravity must grapple with that reality. If you found this exploration fascinating, if you enjoyed this journey through the physics of time, please consider liking this video and subscribing to the channel. Your support helps create more content like this, diving deep into the scientific concepts that shape our understanding of the universe. Leave a comment sharing your thoughts about time travel, about relativity, about which aspects of this topic you'd like explored further in future videos. As you drift off to sleep now, you can rest knowing that you live in a universe far stranger and more wonderful than everyday experience suggests. Time itself is flexible, malleable, a dimension to be navigated rather than an absolute constraint. And while we can't yet build spacecraft to take advantage of extreme time dilation, while we can't visit the past or create wormholes, the theoretical possibility remains. The universe allows it. The physics is sound. It's just the engineering that defeats us. Tomorrow, when you wake, you'll have traveled through time in the most ordinary way, experiencing roughly 8 hours while the universe aged 8 hours around you. But now you know that this 1-to-1 ratio between your time and external time isn't fixed or fundamental. It's contingent on your velocity and position in gravitational fields. Change those and you change how fast you move through time. You are, in the most literal sense, a time traveler, moving from past to future at 1 second per second. That rate might seem fixed and immutable, but physics says otherwise. With sufficient speed or in a strong enough gravitational field, you could slow your clock, aging less as the universe ages more, reaching future times that would otherwise remain beyond your lifetime. The universe provides mechanisms for this. Nature permits it, and someday perhaps humanity will take advantage of these possibilities, sending explorers not just across space but forward through time, into futures we can only imagine. For now, rest easy, knowing that time, for all its mysteries, carries us all forward. The present moment fades into the past as new moments emerge from the future. Time flows, or seems to flow, and we move along with it, conscious passengers on a journey from birth to death, from beginning to end. But the journey is stranger than it appears, the medium through which we move more flexible and wonderful than our ancestors dreamed. Sleep well, time traveler. The future awaits.